Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you everyone for coming. Today we have Chris Burgess speaking to us, and he is a principal researcher here at Microsoft Research and is in charge of the text mining search and navigation group. And today he's going to talk to us about dimension reduction, and he has a funny story to start the talk with.
Thank you very much, Krista. Actually, it's a sad story. So let me just describe why there are two dates on this. Let me see if I get this thing working here. So I have to start with some thank yous and an apology. The thank yous are to Denny and the MSR streaming video team for getting this set up in such short notice. I asked for this Saturday to do this. And the apology is as follows. On December 11th, there was a workshop I was running at NIPS. And December 12th, there was a workshop I was going to speak at giving this talk. The only problem was it wasn't on December 12th, it was on December 11th. And I didn't find out until late. So I managed to miss giving a talk at a workshop, for which I apologize. If you're one of the people who came to the workshop on December 11, 2009 at 3:30 at Whistler, and you missed it, I apologize. So to make amends, I'm giving a longer and better version of the talk now. And this will be put on the web, and it'll be generally available to the public. So just to warn you all, if you ask questions, they'll be generally available to the public. But please don't stop that from asking questions. I'd also like to thank Guy Lebanon and Fei Shah, the organizers of the workshop. They were very gracious in light of my stupid mistake. It was entirely my fault. And Sayan Mukherjee, who managed to come up with a talk that replaced mine on zero notice about dimension reduction, which is pretty impressive. So, okay, that's that out of the way, hopefully. Let's talk about dimension reduction. So there's something that struck me about this general topic, which is it has three names. Dimensionality reduction, dimension reduction, and dimension reduction. And so in the spirit of dimension reduction, we should probably choose this one. But these two, you tend to see in NIPS papers, and the machine learning guys write these, and the statisticians tend to call it dimension reduction. And as far as I can see, there is, I'm not going to say which of these is statistics and which of these are machine learning, but there's a gap. These communities do not talk to each other, as far as I can tell, as much as they perhaps should. And so that is what inspired this talk. I'm going to talk about some quite old work. The idea is to give you intuitions about the whole thing, and then I'll just finish up by saying the latest work that I found on this material for a particular kind of dimension reduction. So what am I going to talk about today? There's going to be three topics. The first is, if you're going to do dimension reduction of your data, you probably would be well off to estimate the dimension you want to reduce it to. And there are certain methods where you have to input the dimension that you reduce to. So this first part of the talk is just separate from the rest. It only depends on the data, it doesn't depend on the labels. The second part of the talk does depend on the labels in an interesting way, and that's what I want to describe. What I'm hoping will happen in this talk is that you'll emerge with a very intuitive feel of what these things are about, and where they work and where they don't, and what papers to read to find stuff that works much better. That's my goal. Actually, I can use this gadget. So let's start by estimating the intrinsic dimension. So imagine you have data and you have some kind of way of looking at it at some kind of scale, which I've represented by this microscope. And you look at it from very far away. So it looks like a point, it looks like it has 0 dimensions. And then you turn the knob on the microscope and you go a bit closer, and it actually looks like this. So the red circle here is the microscope, what the microscope's looking at. So here it looks one-dimensional. But in fact, if you keep turning the knob, you get perhaps into the noise area, and it looks two-dimensional. So the idea is that dimension really is a scale-dependent quantity, or it can be. In this example, it is. So we're going to explore that. There's a very simple way to estimate the intrinsic dimension of your data called the correlation dimension. And let me just describe it. I mean, it's defined there, but let me describe it in terms of this. So what we're going to do is count the number of pairs whose distance is less than epsilon. and compute that as a function of epsilon, how that increases. Let's just take one xi and make that the middle point of this circle. Then imagine how the number of points increases as you increase the circle. Well, it's going to go up linearly with the radius of the circle, right? Because you're just expanding it across the line. So, and now you do that for every point. And it'll tell you that this data is one-dimensional. You can do the same thing for 2 dimensions. I just choose one xi, and I put a circle around it, and I grow it. This epsilon is the radius of the circle. Then it'll tell you it's 2-dimensional. So this gives you an incredibly simple way to estimate intrinsic dimension. Now, it has some problems, and I'm going to be very upfront about the problems of these methods. But that's the basic idea, is that you expect this quantity, this count, to be proportional to the radius to the d. And notice it doesn't matter what the density is. If this is half as dense, the density actually multiplies here. So if you take the logs, the density will go away. And what you want is your d is the slope of the log of the counts versus the log of the radius. So that's the idea. Now, some of you may be worried, and you should be worried, because high-dimensional data tends to be equidistant. It's not really true, because otherwise I wouldn't put it in quotes. But let me just say what I mean by that. So consider the regular simplices, right? Here's the simplest regular simplex. It's a point. Here's the one-dimensional. Lives in a line. It's got 2 points. Lives in a plane. It's got 3 points. You can keep on adding a point to a simplex to get another simplex in one higher dimension, such that every point is distance 1 away from all the others. If your data looks like that, this ain't going to work. Because what will happen, I'm not plotting the logs here, just plotting the counts, you'll have 0 counts, and suddenly you'll get them all, and then you'll have 0 growth. So if data tends to be equidistant, it's going to make this tough. One thing that I think is an advantage of this method is that it just looks at where the data points are. It's not like trying to tessellate the space and estimate the direction that way. Here's a sort of continuation of the caveat. So imagine that your features are in plus or minus 1 in d dimensions, and they're zero mean, and they're IID. They're probably not very good features if that's the case, but possibly not. Then the expectation of the squared distance between 2 of these vectors, these d-dimensional vectors, is 2d. Right? Because each vector squared is just d, and the product expectation has 0. So you can use Hoeffding's bound to give a bound on the deviation of the expectation from its mean. And that's what this is, but this is just expanding this quantity in terms of the dot product. So I have d random variables with expectation 0. So what this is saying is that for a given fraction of your dimension here, it actually increases exponentially in d. So the probability is actually pretty high that you will exceed this bound. If Epsilon's 0.2 and d is 500, but it's extremely small if d goes up to 5,000 still for that value of the fraction of the dimension that you're looking at. However, we're going to rest our faith and hope on our features not being IID, and note that kth nearest neighborhood works even in high dimensions. So there is structure in the data in high dimensions that we hopefully can estimate. All right, let's do a sanity check. Let's try this on a piece of data. There was a much nicer picture of this sphere, but it took too long to load if you do it straight from that. So this is just data uniformly on the sphere, on the 2-sphere. And what I've done is plot what I mentioned before, log of the count versus log of epsilon. And the blue is the data, and the red is a straight line fit. And of course, we get a very nice 2-dimensional plot, even though you're looking at a 3-dimensional figure here cast into 2 dimensions. That's why it looks thicker on the equator, or whatever you want to call that. So here's a puzzle for the reader. Why doesn't this level off here? It should go to 0. So if you, that's just a puzzle. I'm going to leave that as a puzzle. Let's throw something slightly harder at it. Since it's this time of year, we're going to throw a snowy sphere at it. So the North and the South Pole. Now you're looking through the sphere. So there's more data at the north and more data in the south. It's just a different way of sampling to get this distribution. And now it's not quite as good. If you compute the plot, the straight line fit to the whole plot, you get something way less than 2. But as you go down to 0, these distances are ordered, by the way. right? Each point here corresponds to a distance between a pair of points. All such distances have been computed. They've all been ordered, and that's what's used to generate this plot. So down here, I'm looking at the smallest distances, and that's what you want to do to get the local estimate of the dimension if the data has local intrinsic dimension. And it does climb up to 2 as you go down in the number of data points. So that's encouraging. So let's throw Gaussians at it and see how it does on those. So these are 50,000 points, spherical Gaussians. And what we expect to see is that, this is again the plot of the slope of what I just showed you. So a flat part at 2 says the dimension, it's estimating the dimension to be 2, and then things over here are dropping off because everything's getting too far away to make a good estimate. So 2-dimensional works fine. 5 dimensions, well, it's okay. It does sort of peak at 5. 10 dimensions doesn't quite get there. So it doesn't tell you that the data is 10-dimensional. And then 50 and 100, it begins to fall off far too rapidly. Let's have some fun. So a couple of times in this talk, I'm going to apply this to real data. And the real data is going to be ranking data, because that's what I'm sort of familiar with. And I would like to learn more about it. So let's try and see what it says about our ranking data. The ranking data, this is the Bing ranking data, excuse me, has 501 features, 500 queries, and for each query document pair, you get a feature vector. So there's 69,000 feature vectors we're talking about here. And that means you've got about 2.4 billion pairs, which is interesting. If you count compared to the number of pairs you get when you train one of these things from the labels, that's why training pairwise works, because per query labeling, the number of pairs per query is far smaller than the total number of pairs you could ever compute. So then we're going to compute all of these distances. We're going to sort them using a cool tool that TMSN has for sorting huge data sets. And then I'm going to average, because 2.4 billion is a bit much for MATLAB, we're going to average using a block size of 100 points of these sorted distances, right? And that'll give me about 20 million points. So we get something pretty nice. Looks like there are several intrinsic dimensions. There's perhaps one here and maybe a slightly higher one here. Remember, it's the slope of this curve that we're looking at. And then it sort of goes up. And then what you'd expect to see, it flattens down to 0. It's like that point in the first slide I showed you, the microscope looking at just the point. So that makes us feel nice and warm, except it's not true. If you now plot the points instead of lines between the points, what was here was a straight line is actually just 2 points. So that little flat part that I thought might be some intrinsic dimension is certainly not. And in fact, everything between these two slices is only 50 points. OK, well, let's assume that the data is sort of clustered around here and fit a straight line to the straight line bit that we're expecting to measure the dimension of this data. Don't forget, this data starts out by being 500 dimensional. Again, it doesn't work. It's a pretty lousy straight line fit. And the reason is that the data is not uniform across this line. From here to here, you have about 100,000 points. And from here to here, I don't know if you can see these lines, you have about 3 million points. So the data is all bunched up here. So when you do a straight line fit, you're going to get a straight line fit to this. So let's actually look and see where the data is by overlaying the histogram of where the data is. And of course, that's where most of the data is sitting up here. But let's press on and see if we can estimate a dimension with this by computing the slope of this thing. Now, what I'm showing here is the same graph I had before on the left. And on the right is just the slope. And as you can see, it's an extremely noisy thing, bounded above by about 5, but very noisy. Why is it so noisy? Even though this has been smoothed by 100 samples per block. Well, if you just say, take some point, the 20 millionth, and then plot 5,000 of this graph, you get a very ugly looking thing. Well, maybe it's not ugly, but so you should probably smooth over several thousand points to get a nice smooth curve. But we have 2.4 billion, so that's OK. So here's what you get if you smooth over 10,000 points. I take 10,000 of these distances, I take the average, that's the distance, and I compute a nice smooth gradient. And again, it doesn't really have a flat part, but it says it's around somewhere less than 10 is the intrinsic dimension of this data, perhaps. modulo the problem that we may be missing it completely. But it's interesting to try that anyway. So as far as correlation dimension is concerned, my conclusions are, there's this strong trade-off. It's kind of useful if you're looking for low-dimensional spaces. But there's this trade-off between the drop in density as the distance increases in your data and the scale dimension estimate. And it looks like you can underestimate the dimension with those Gaussians, for example, for that reason. Something else that might be worth thinking about is if you think your data is on a manifold, replacing these distances with the geodesic distances using k-nearest neighbor like ISOMAP might work better. How might one use this? Well, suppose I have click features in my ranking data and other features, and I remove the click features, and I get a different dimension. That's telling me something interesting. I haven't done that here, but it's one possible way to just see where the dimensions of your data are coming from if you can group your features into interesting groups. OK, so that's the end of part one. Now we're going to switch gears and look at methods that depend not only on the data that you have, the feature vectors, but the labels, too, of the feature vectors. So far, we haven't talked about that at all. So I want to say what sufficient dimension reduction is in a general sort of way. So you have a variable, which is the label, which we'll take to be just one-dimensional throughout this talk. And your data lives in RD, so it's just feature vectors. And it's distributed according to some distribution. And the goal is to find a map that maps RD down to RQ such that Q is much less than D. So this is the dimension reduction part. And such that Y given X has the same distribution as Y given this map of X. Okay, well, we'll go into more details what this all means in a minute. But it's kind of interesting there's sort of three ways to look at this, and they're equivalent. If such a P exists, then X given both Y and phi of X will have the same distribution as X given phi of X, and that's called inverse regression, which is what I'm going to talk about, because it's so simple to try. Then there's forward regression, estimating Y given X, and that'll have the same distribution as Y given phi of X, just by definition. And then finally, sufficient reduction, Y and X are independent given phi of X. So there's this kind of nice statistical way of looking at this whole business. So why might want to do this? Well, first of all, I think what drove it in the statistical community early on, at least, was visualization. Certainly, if you can get down to just a few dimensions, you can see a lot of stuff, in your data. If you can get down to 2 or 3 dimensions, you can see what it looks like. And you can still directly visualize if the low dimensions are dominant in some way. Let me give you a very concrete example that I haven't listed here. Suppose you have a ranker, say, for Bing, and it has 500 features. And you do this, and you find that the outputs of your model really only depend on 2 linear combinations of the features, or 2 features, or some small number. That's very interesting, and especially if those features are subsets of the features you started with, because then you'll know that you can get rid of the features that you don't need and retrain and should be able to get the same results. So that's another application, possibly. It could also be a linear combination of all of your features, and then it's not so easy. But in general, people are using this kind of stuff to find small subsets of predictors that account for whatever response they care about. And it's used in biostatistics for gene expression, for example, by these folks. So an equivalent way of looking at this is that the model that we are thinking about is that there are some projections. These are just vectors. And the function that you care about is some unknown function of these unknown projections of your vectors with some unknown noise. But you're assuming that this noise is independent of the x's. So that's the basic. Think about this model for the rest of the talk. That's kind of what we're trying to get at. We're assuming that it has this form. We want to find these a's. So these a's actually span the subspace you care about. It's just the projections of the data onto these a's. This is the transpose. Think of them as unit vectors. That's what we're trying to find. That's what we're going to call the central subspace. If we can find all of these a's, right? That's what is called the central subspace. This is kind of interesting because we're not saying what f is. F could be anything. And yet we're still saying we can find out what these a's are. And it's also ill-defined because I could redefine f and redefine the a's and have the same problem to solve, and yet this stuff will still work. So we're going to call the central subspace spanned by the A's SA. And that's what we want to try and find. And I'm just going to give you I'm going to try and give you intuitions and lots of little experiments showing how this stuff works now on this stuff. This is called sliced inverse regression. So the basic point for me is it's much easier to estimate the expectation of x given some y than to do the full regression, which is what this would be. So here's a theorem that sort of underlies this, and here's the sketch of the theorem. We're assuming this model that I just described, and we're going to center it so that the expectation of x is 0, and it has unit covariance. It's going to whiten it. And we're going to assume that x alone, not dependent on y, just the x's, are elliptic distributions, by which I mean simply that the contours are ellipsoids. Gaussians are elliptic distributions, for example, but there are others too. If you have a distribution that's elliptic, it turns out that the expectation of x with respect to, given that the values of these guys, lies in this subspace. So that means that, so the theorem says then that the expectation of x given these labels lie in the central subspace you care about. So that's kind of cool. You can get to the central subspace this way, doing a pretty simple computation, which I'll just describe more, and getting these E of x given y's. However, it's not guaranteed to identify the whole subspace. It's just guaranteed to be in the subspace. So what is the algorithm? It's incredibly simple. You're going to whiten the data to begin with. This is how I run it. You can do it other ways. We're going to bucket the data into n buckets by the value of the output, whatever that is. So I'm assuming here, for example, there's a bunch of outputs, not just like 3 classes. If there's 3 classes, you only have 3 buckets. You can only possibly estimate 2 dimensions using this technique, for reasons I'll describe in a minute. But if you have regression data, then it's a different story. For each bucket, and that we're bucketing by the values of the outputs of the model, or not the outputs of the model, just the y's, the responses you're given. I'm going to compute the mean for that bucket. And then we're going to compute a weighted sample covariance. So replace all of those data points by their mean, and then compute the covariance of those means. There's no minus overall mean here because we whitened it. So the overall mean is 0. So we're going to compute this covariance matrix of the kind of means data. In each bucket, replace the data by its mean, compute the covariance matrix of those guys. That's what we got. Compute the eigenvectors of this. And then moving back to this space, which is not whitened, this is your subspace. So let me try and throw a bit more intuition on this. Imagine you have some data. This is actually ranking data that we'll come back to in a minute. And again, we have this model. And just suppose that it depends only on the first 3 x's in this way. But we don't know what f is, and we don't know what the a's and a1 and a2, a3 is. I'm choosing the ranking data just as a kind of toy in the sense of it's a model that I have that has output these outputs. And it'd be really cool if these methods could actually reverse engineer the neural net that generated these things and tell me it had 10 hidden units. Because if you think about it, a neural net's exactly this. It's taking a linear projection of your inputs, mapping them to a hidden layer, and then doing something on top. So, can it recover the structure of the net? So imagine, I'm just writing here the x's that y depends on. Okay, just imagine that's the case. Then if it happens to be true that the expectation of all of these other guys, well, actually it is true, because these guys are independent, we're assuming. And so the expectation of these x's, given y, is the same as the expectation of these x's, which is 0. So if roughly speaking, the expectation of these guys, given y's, is not 0, you're going to find these a's. You're going to get that dependence. That's just kind of hand-waving intuition, I hope, to help you understand what this is doing. There is a problem here. If your outputs, your responses, are symmetric, then here's an example. These expectations will vanish, even though the central subspace here is one-dimensional. You won't find it. So we'll come back to that in a minute, but let's proceed. There's another kind of question. How much binning should we do? Right? So what we're going to do is we're going to bin the data by the values of the outputs. In each bin, we're going to compute this mean, and then we're going to compute the covariance of those means. Well, if you bin everything, if everything gets its own bin, which is not quite the case here because there's 30 guys in this bin. But if everything got its own bin, you'd be doing PCA, right? You'd just be doing PCA on all the data. If you put everything in one bin, actually the covariance matrix will vanish. So there has to be something in between that's better, hopefully, right? And one question with these methods is how sensitive are the outputs to the choice of bin sizes? So let's try this on some Troy data and see what happens. So I'm going to take 100,000 points. They are generated from a spherical Gaussian in 50 dimensions. I have binned them with 120 bins here. And here is my dependence that I'm trying to uncover. Right? I imagine that you don't know that y is x1 plus x2 plus x3. It could be plus 5x49, plus 10x13, but we don't know. But that's actually what it is. So if you go ahead and apply sliced inverse regression to this using these bins, you get that the largest two eigenvalues are these. So it's saying, yeah, there's one direction. And your subspace is one-dimensional. That's the eigenvalue. There's a huge drop in the size of the eigenvalues. And the principal eigenvector tells you that roughly each of these z's have the same weight. So it really nailed it. And if you take the principal eigenvector of the principal component of this thing and project onto it, you recover this straight line. So that worked beautifully. It should, right? I mean, that's kind of one of the simplest things to try. Let's try a slightly harder functional form and see if it can uncover this. So the same kind of setup. I have 100,000 points. They're spherical Gaussians. I've got my outputs are defined by this function, which is kind of a nice function because for large x2 positive, it becomes linear. And for very large negative x2, it becomes linear. So it's kind of linear. And we know it works for linear, right? So this should be pretty benign. And it sort of gets it. So now, I mean, there are statistical tests that say how much the eigenvalue should drop for you to, with what confidence to say the dimension is such and such. But here it's dropped. So it's dropped by a factor of 100. So, I mean, that's pretty clear that something's happening. And we have two dimensions here. And these are the first two eigenvectors. So it does indeed pull out x1 and x2 as what you want. And then if you project the data against this first eigenvector, this is what you get. So again, it seems to work OK. But I have to say that when I prepared this talk, a lot of stuff I tried didn't work. And I was trying to find good examples of things that worked, and I kept finding good examples of things that did not work. So let's see something that doesn't work at all. Here's another functional dependence. It's a perfectly fine functional dependence. Again, it's just got two variables. Y is z1 plus 5 sine pi of z2. And I chose the 5 here just to get a nice kind of wiggly graph. You can try other things too. But if it's too flat, it'll obviously find a one-dimensional space if this period is too long. So how does sliced inverse regression do on that? Well, here's the histogram. And remember, each bin, we're going to take the mean of the vectors that fall in that bin and then compute the covariance matrix of all those means and then do PCA on that. It just sees one direction. In fact, x1, it completely missed the x2 dependence. And that's the eigenvector. So at least it got that x1 is there. OK, maybe that was too hard. Let's try something a little simpler. We'll try a model y as x1 plus x2 times x3. Can it uncover this structure of the problem, right? Well, it doesn't really at all. Again, it says x1 I get, but the other eigenvalues are all pretty small. And there's no sudden drop-off from x2 or x3 to x4 compared to the drop-off from x1 to x2. So this is just uncovering the one-dimensional space. So that's where SIL is not working. So now we're going to try a method that actually appeared in a comment by Cook and Weisberg to the paper that proposed SIR. And the point was that sliced inverse regression depends on these means, right? So it's a first moment method. So it's going to miss these symmetry problems that I described, right? These expectations will be 0 for those. And notice the following. So suppose you've got a projection operator to this central subspace for the z's. And this is the projection operator to the orthogonal space. And it turns out if your x's are elliptic, then your covariance matrices satisfy this equation, which is just taken from this paper by Cook and Weisberg. And what's interesting, if you just rearrange terms, is that this quantity here, and wy is 1 if the x is a Gaussian, or it's just a y-dependent number if they're not. So just imagine wy is 1. So you've got the covariance you care about, and these projection operators to the central subspace that you care about, and the projection operator to the orthogonal subspace. then this thing here actually lives in the subspace because it's equal to its own projection into that subspace. So that means that if I took that and found its eigenvalues, eigenvectors, I should be pointing in the space I care about, right? Well, what they took instead was the square because they wanted positive eigenvalues. So what they've written down here, actually, this is replacing what SIR was just this covariance matrix of these bucketed means. This replaces that. It actually is a kernel. It has positive, it's positive semi-definite. The ni is the number of samples in each bin, and ni is the total number of samples. So we should be able to make some headway with that. So let's take a look and see how this is what the algorithm would be, or is. Again, you whiten the data. You're going to again bucket the data. But instead of computing the means in each bucket, we're going to compute the little covariance matrices in each bucket. And then we're going to compute this weighted kernel of these little covariance matrices, one for each bucket. And we're going to weight them by the number of items in that bucket. Obviously, if you've got a bucket with like 3 items, you don't want to weight its covariance matrix as highly as one with 300,000 items. And again, just normalize by dividing by the number of points. Same kind of thing. Compute the top eigenvectors and output AK. So here, this is kind of a busy slide. This is a rather short talk. I should have mentioned it's a half-hour talk. So, but let me describe it. This is kind of sliced inverse regression versus sliced average variance estimation. So we saw that for a nice linear dependence of your outputs on the x's, sliced inverse regression nails it. The first eigenvalue is huge and the rest are tiny. It's saying this is a one-dimensional space. And the first eigenvector says, yeah, and it's x1, x2, and x3. Right here, so that's great. Sliced average variance estimation doesn't get the linear dependence, because it's the second-order method. But it does notice that x1, x2, and x3 are the 3 variables that matter, at least. But it overestimates the dimension, actually, here. All right, so let's see if that, remember that spherical, the symmetry problem that sliced inverse regression could not detect? Let's just check that. So if you do a sphere, so now y is equal to x1 squared plus x2 squared plus x3 squared, then these are the eigenvalues. And so there's absolutely no indication what the dimension of the space is, or that y just depends on these 3. Perhaps there is. Perhaps there's a bigger gap here, but it would be a tough sell, I think. Right? So I'm saying that, if this was working, these 3 points would be much higher than all of these points. It has, however, found the x1, x2, x3 dependence, because these are the first 3 eigenvalues. Sliced average variance estimation nails it. So it says, yeah, x1, x2, and x3 equally important, and here are the basis functions for your space. It spans a 3-dimensional space. You can span a 3-dimensional space in many different ways. This is just one choice that the system chose. And remember x1 plus x2, x3, a fairly simple thing, but sliced inverse regression didn't get it. It says, yay, x1, one-dimensional space, which it got. It got x1, but then the others are just random if you look at the next 2 eigenvectors. Sliced average variance estimation does a much better job. It says, yes, x1, x2, and x3, and yes, indeed, here are the 3, x1, x2, and x3, spanning the space you care about. So this one, SIR worked, save did not. Here, save worked, SIR did not. Here, save worked, SIR did not. Here, they both work. This is one that I mentioned before. They both look quite similar, actually. So it's saying, yeah, x1 and x2 are your dimensions. And finally, here's one that neither of them works. They both think it's just a one-dimensional space because the eigenvalues are so big compared to the rest. Let's just try it in our ranking data and see what happens. So remember, this is the histogram of the outputs of the neural net ranker. 100,000 samples, 110,000 for 1,000 queries. And this is what you get. So I think if these things were finding the 10-dimensional space, now it could be a lower dimensional space. Remember these networks, the network that I trained to generate this data has 10 hidden units. So it's really a mapping to a 10-dimensional space. But the eigenvalues drop off fast, but there's no obvious cutoff, perhaps. So it's saying that the dimension could be less than 10 of these things. If you take the principal component of the sliced inverse regression, then you get a fairly nice dependence, actually, of your data projected onto that direction. And this is a very complex, a neural network can model all sorts of complex functions. But this is fairly nice and linear. However, this is the eigenvector corresponding to that projection. So it doesn't tell you anything in particular. It's just saying this particular projection is very nice and linear. So just to finish up, actually, what I've talked about today is old stuff, but I hope I gave you some intuition as to why it was interesting and how it works. It's very simple old stuff. Certainly worth trying if you are trying to solve this problem. However, there are more recent, much better methods. So Cook recently came out with maximum likelihood-based method to solve the same exact problem. And that actually will compensate for both of the deficiencies in SIR and SAVE. And then actually in NIPS, so there is some people that are interested in this stuff in the machine learning community. There's a localized sliced inverse regression method which uses k-nearest neighbors to kind of localize the SIR computation, and it's more robust. And then, as you might imagine, it's easy to kernelize these methods. And so the next 3 papers are people working on the kernel version, which is much more general. So I think if I was going to apply this in earnest, I would probably try this. Actually, I'd try. This is extremely easy to try. This is you have to write some code, write a bit more code perhaps. And these are actually relatively easy too, I think. That's it. Thank you very much. Yes, Sumit.
So when you had the plot of the eigenvectors with the various functions combining them, it seemed like a slide that appears in many other talks that leads to kernelization, because you're reaching this point where it's like, well, okay, I've got some first order stuff, first order method catches it, the second order stuff, second order method catches it, and then as things get more complicated, I need something that really generates higher order moments, like some kind of kernel. So I'm curious that, I don't know if you played with any of them, but like the kernel-based methods, are they much better at recovering the inherent?
They claim to be. I haven't played with them myself. I just wanted to really nail the kind of the history here, actually, tutorial. That is the motivation. You're exactly right. There's always the question of how to choose the kernel and what's the right thing to do there. But you're doing something linear in a high-dimensional space. That's a nonlinear mapping from your low-dimensional space. So yeah, they could work very well.
Well, I guess the hope would be that, what you saw was that when you introduced the second order method, it wouldn't falsely, it would still be fine with the first order problem as well. And so that even if you had a higher moment generating function, you would still be able to.
That's probably true, but it's also true, I believe, that the likelihood methods, which is so that the likelihood methods of the statisticians doing that, continuing down this path, and they are much better too. They solve both of these problems, the first and the second one. More questions? So thank you. Oh yeah, Mikhail.
Classification tasks, I always found that neighborhood component analysis, the older row-based, works extremely well if you have enough data and you regularize it. And it's super flexible in the sense you can learn arbitrary complex manifolds, just whenever.
Yeah, it's a powerful method. Yeah.
You kind of more concentrated on regression, I guess, because.
Well, this is don't forget this is dependent on the outputs, right? So if you did dimension reduction without the outputs, like through PCA, you wouldn't see any of this behavior. It would all be just, it's all spherical Gaussians. So the key thing is in the sufficient dimension reduction that all you care about is what variations in the data, what variates determine the variation I'm seeing in my response, in my outputs. Right? So that's what we're trying to model here. Yeah.
Suppose it's a classification problem that I'm trying to solve. Then I don't really have, that kind of, the continuous outputs. So is there a way we can modify these methods?
I believe so. So another direction, actually, that I didn't put up here is by Jordan and Shah and others. Another sort of approach to the kernelization of these methods. A very general approach. And I believe that does get around this problem. You're exactly right. If you have a classification, any kind of data where you, for example, clusters or classes, you only have n classes, then the rank of the covariance matrix we're talking about is n-1, so you're stuck. You can't get more than n-1 dimensions out of that. So this method by Jordan and I think Francis Bach, maybe, hope I'm right, but certainly Jordan and company, does solve that. but I haven't investigated it myself.
What would be an intuition? I'm just wondering, right? When you can't bin your data anymore.
I'll just refer you to the paper. I know that it gets around that problem. How it does it, I forget. But,
and also, like thinking in terms of isomap-like methods, right? So instead of just thinking order 1 or order 2, can we use k nearest neighbor or epsilon ball methods?
yes, in fact, that's exactly what well, don't forget, isomap is not doesn't have any dependence on the y's. It's just the data, modeling the data. But yes, that's exactly what's going on here. That's exactly what they're trying to do. They're inspired by isomap, and they're doing k nearest neighbors in each bucket, and it turns out to be rather more, they claim, flexible and powerful than sliced inverse regression alone. So yes, you can do that, and it's very simple. If you want to try something like that, I would start off. If you want to try simple first, this is awfully close to sliced inverse regression in terms of ease of computation. You do need to do k nearest neighbor, which is a bit expensive, though. All right, thank you very much, folks. Thanks for coming.